Hey everyone, welcome back to Everything is Relative with me, Mr. K. Today we're going to be doing a crash course on the topic of electricity for Cambridge AS Physics, and this is the precursor to the topic of DC circuits, which is a bit more involved. But here we're just going to talk about the basics of electricity and electric currents and the different quantities associated with electric currents. So again, this is just a crash course, and it's only going to be a brief outline of the important concepts that you need to know when studying the topic. So the first thing we study when we talk about electricity is, as some of you may know, the electric current. Now we have to define what an electric current is and then talk about how we measure it. So let's assume that we have some solid object, matter. Anything that has mass we refer to as matter. And we know that matter can be, if we zoom in, we break up this matter into its constituent components, which is initially a nucleus, which is positively charged, which contains protons and neutrons. And because the protons are positively charged and the neutrons are neutral, it makes the entire nucleus of the atom positive. It's a dense nucleus. It's very small in comparison to the size of the entire atom. And around the nucleus, we have, well, let's assume these things are whizzing around. Well, they are whizzing around, but not so much in an orbit as I've drawn them, but these things are electrons, much tinier than the things in the nucleus, much lighter and much smaller. And electrons are negatively charged. And if I go down, if I zoom in further so that I focus only on the electron and I exaggerate the size of the electron. So here's my electron. Believe it is or not, it's very tiny. It has a negative charge. Remember, this is just by convention, but electrons are negatively charged, minus 1.6 times 10 to the minus 19 coulombs, where coulomb is the SI unit for electric charge. And the thing about this charge, and we sometimes give it the symbol minus E, the lowercase e for the word electron, and E is the elementary unit of charge, 1.6 times 10 to the minus 19 coulombs. We call it the elementary unit of charge because what we realized is that all charge is quantized. Any charged object, any charge, must be a multiple of 1.6 times 10 to the minus 19. Meaning we can't have half an electron or 3/4 of an electron. There must be an integer number of electrons or positive charges in the other case, which means that the charge must be a multiple of 1.6 times 10 to the minus 19 coulombs. And the reason why electrons are usually our charge carriers is because, well, they are small, they move easily, and also they exist in states in metals which allow them to move quite freely. They exist on the surface of metals and they are sort of delocalized away from their nuclei. So metals are going to be our main focus. Again, this is a topic on electric currents, and we know that electric circuits have wires that are generally made from metal. And metals have free or mobile electrons. You may have learned this from chemistry or IGCSE physics. But these free or mobile electrons, since they are small, don't require a lot of energy to move and hence carry charge from one place to another and hence carry energy. So what happens is a battery or a cell provides the energy for electric current and allows electrons to drift in a metal, in a wire, and electrons drift towards the positive terminal. Remember, batteries have a positive terminal and a negative terminal, and a battery will just give the electrons a kick. We'll talk about how this kick comes about in the next crash course on DC circuits, but the flow of charge the flow of these electrons constitutes an electric current. So when charge is moving, when charged particles are moving, and they move in a sort of consistent manner, we say that's an electric current. So if I were to just draw a very badly drawn rough idea, here's a battery. I know this is not the circuit symbol for a battery, but I just want to make a point. And then I connect a metal conducting wire to this battery, and then I have some resistance. In this case, I'm going to use a lamp that's meant to be circular, but it's a battery connected to a lamp. And you can see I've clearly labeled the positive and negative terminals of the battery. Then what happens is the electrons begin to move in the circuit. They are moved away from the negative terminal of the battery, as they themselves are negatively charged, and the negative charges will be repelled from the negative end of the battery. They move around the circuit, through the lamp, and then back to the positive end of the battery. And so now we've created a current. Since charge is flowing, since we have negative electrons moving in the circuit, we have an electric current. So simple enough, but a more complete definition of current is the rate at which these charges are flowing. So it's the rate, and I'm probably going to summarize this, so it's not a full sentence, but it's a rate of flow of charge through a specific point or past a point in a circuit. Because remember, I can connect an ammeter, which is the device I use to measure current anywhere in the circuit, and measure the current at that point in the circuit. We know that for this series circuit, the current will always be the same, but we have to choose a specific point where we're measuring the current, and the rate at which the charge flows past that point is called the electric current. And this is equal to the amount of charge, which is denoted by the letter Q, divided by the amount of time, denoted by T. And so what we get is, I'm going to use square brackets to denote units of measurement. The unit of measurement for electric current, which we give the symbol I. Probably just write this down. Don't get confused between current and charge. Charge is measured in coulomb. And the unit of measurement for the current I, as you can see, is a coulomb per second, which is too much to write, so we write it as an ampere. Okay, and the ampere is denoted by a capital A. So we measure current in amperes. And from here, with not so complicated mathematics, we see that Q is equal to I times T. And so we have to kind of present another convention. Initially, very long ago, when we figured that current can actually flow in a circuit, it was thought that current was the flow of positive charge. And so, to stick with the convention that lasted very long and has become quite the norm, we assume that positive charge is flowing in a circuit. And we call this conventional current. We know now that it's actually the electrons that are flowing, but initially we didn't. And so we just assume that positive charge is actually flowing in a circuit. And so does it change anything in our circuit? Well, it just changes the direction of current. So if someone were to literally ask you in what direction is the current flowing, that question in physics tends to mean, well, in what direction is conventional current flowing? So if I show you the same battery, conventional current, which we are going to use unless otherwise specified, means that instead of negative charges, we have positive charges, which we know is not true, but we just do it that way anyway, and they flow to the right. And you can see that in this case, electrons will still flow to the left. So essentially, nothing is fundamentally changing besides our convention. And well, if we zoom in even further and we get more three-dimensional, and I say, hey, is there anything else I can say about this current? Well, let's say I have a wire, and I'm going to say, well, let's not just assume that this wire is one-dimensional like I have so far, but this wire is in fact three-dimensional. It has a surface area, capital A, and then I have in this wire electrons, mobile electrons that are free to move, mobile charges rather. We won't say electrons because we're going to assume conventional current, but these mobile charge carriers can move, well, they can move in all directions, but they have a tendency to move in one direction along the wire, and that depends on how your battery is placed in the circuit. So all I've done is taken this wire from the diagram above and blown it up and zoomed in. Well, these electrons, it turns out, actually have a drift velocity. So on average, they move in one direction. In the case of the diagram above, from right to left, they move with the average speed of v, which we call the drift velocity. And so if this wire has a cross-section or a cross-sectional area A, and the number, this is an important quantity, the number of charge carriers per unit volume we call little n, right? This is also known as the number density. So the number density of charge carriers. How many charges are there in a unit volume? We call little n. The charge of each of these charge carriers will be the same. They're all identical charge carriers. In the case of electrons, they all have the same charge, and that charge is q. And the speed at which they drift on average obviously will be the same for each of them with a consistent current, with a constant current, and we call that speed little v, just like v that you used for velocity. And in another video, I'll prove, or I'll derive this equation, but what we get is a very important expression. You need to know this. The current I is equal to the cross-sectional area multiplied by the number density of charge carriers multiplied by the drift speed v times the charge q. So I is ANVQ. A little bit of an abstract equation. When we derive it in another video, it might make a bit more sense. But that's an equation for the current if the wire is now no longer one-dimensional but more three-dimensional, as we've shown it. Now, besides current, are there any other quantities that are important in electricity? Well, yes, the potential difference. Again, this one is a bit of a misunderstood concept. And you need to understand potential difference when we are working with the topic of DC circuits, which will come next. So the first thing we know is that a cell or a battery is actually allowing charges to move around the circuit. But what does the cell actually do? Well, the cell provides a potential difference. And obviously you can see the word difference implies that there's a quantity called potential. And you will learn about potential in A-level physics when you study electric fields. But basically what a battery does, since it has a positive and negative terminal, is it creates a potential difference. It's basically separating positive and negative, allowing charges to move in one direction around the circuit. And by definition, since it is allowing, quote unquote, allowing charges to move around a circuit, the potential difference must be doing work. It must be physically pushing these charges around the circuit. Again, this may not be totally conceptually correct, but the idea, this way of conceptualizing it, actually does work. So we can say that the potential difference between any 2 points in a circuit is the work done per unit charge, moving the charge between those 2 points. So how much of energy is given to a coulomb of charge as it is pushed between 2 points in a circuit? And we give it the symbol V, and we can say V is the work done W divided by the charge Q. And as you can see, the units of measurement for the potential difference, sometimes called a voltage, we can use those words interchangeably, is obviously the joule per coulomb. But it's also the derived unit of the volt. And it might be a bit late to go back and do this, but I didn't write this before, and I here is measured in this uppercase. A is the ampere. Remember, it is named after someone called ampere, but when we write it as a unit, it becomes a common noun, not a proper noun, and so there's no capitalization on the first letter. So the ampere is a lowercase a. Volt is also named after someone, but with the lowercase v. But in that case, the full name wasn't volt. So it's one of the few, in fact, the only quantity that I know in which the symbol for the quantity and the symbol for the unit are the same. Be careful, this doesn't happen very often. So the quantity and the unit have the same symbol, V for potential difference and V for the volt, what we measure it in. And so what does a volt actually mean? Well, it simply tells us that if I have a coulomb of charge, how much of energy I am giving that coulomb of charge to move it around a circuit. And the thing I use to measure the potential difference is called a voltmeter. So an ammeter is used to measure current, a voltmeter is used to measure, well, voltage or potential difference. And from here we can see that W is equal to V times Q. So the work done in an electric circuit is the potential difference V times the charge Q. So it's actually not difficult to calculate how much of work is being done by a cell in a circuit, or by a power supply for a house, or any sort of load. And while talking about power, we can discuss power a little more in detail, because the next thing we need to know is what is electrical power and how is this relevant to whatever we're studying. Well, remember that from dynamics we said that power is the rate at which work is done. But hey, we did say above that work is being done by the battery moving the charge around the circuit. So the rate at which work is being done, power is W over T. But wait, there's a W in the equation above. V is W over Q. So I can do a little bit of mathemagic, and I can rearrange the equations, and I can find that P is equal to QV divided by T, since W is equal to Q times V. And this is equal to V times I. Why do I say that? Because remember, the rate at which charge flows through a point, Q over T, is equal to the current I. And so power is equal to the potential difference times the current passing through a certain device in a circuit. And just like in dynamics, the unit of measurement for power, again I'll use square brackets to denote unit of measurement, is the watt, uppercase W. So the energy carried to a circuit component, a specific component in a circuit, is equal to the potential difference across that component times the current through that component. So again, I'm drawing a battery. We learn in the next topic that that's not actually the circuit symbol for a battery. I'm going to connect an ammeter, which is always connected in series in a circuit. Again, we'll cover that in the next crash course on DC circuits. And I'm going to connect a lamp in the circuit. And so in the circuit, I have a current I. I is the same everywhere, does not change. I have an ammeter to tell me what the current I is. And then I have a lamp. So there's energy being given to the charges in the circuit, and some of that energy gets transferred to the lamp because the lamp has to turn on. It has to generate light and a little bit of heat. Okay, and so if I connect a voltmeter across, remember I must connect my voltmeter across two different points in a circuit, that is before and after the lamp, and I can tell how much of energy is being given to the lamp by using the equation power is V times I. So I can tell what the power output of the lamp is, and by increasing the potential difference V, increasing the current I can increase the power that is given to the lamp, and hence the lamp will shine brighter. And so this is how electrical power applies to the components of an electrical circuit. Another quantity that we have to cover is that of resistance. Again, it might be familiar to some of you, but the word resistance, as you can see, means to oppose something. So what is the quantity of resistance? Well, the quantity of resistance is the opposition to current. When we have a circuit component that doesn't really want current to move through, but current usually moves through anyway. Like our lamp in the example above is a form of a resistor. It actually makes it more difficult for current to move through. The charges themselves rather lose some of their energy to the lamp and have to gain that energy back by moving through the battery. And so this lamp has a resistance. Now, insulators, things that are traditionally insulators, electrical insulators to be more precise, have a high resistance. They don't like current flowing, and hence insulators can't be used in a circuit. We wouldn't use a plastic for our wires. The resistance is a bit too high. Then we have conductors, which obviously have a low resistance, like a copper, for example, which is mostly used for wires. If you go to your lab, you find that your wires are mostly copper. And metals generally have a lower resistance, and they allow electrons to flow, and we therefore call them conductors because they conduct an electric current. And then we have things like semiconductors, which are not as good at conducting as conductors, but they can be made to conduct under special conditions. So semiconductors have their applications in electronics. Now, the resistance is equal to V over I. So this will actually be covered in the next topic, but the resistance is V over I. And what this means is if I keep the potential difference constant, the potential difference across the circuit component, what that means is an increase in R decreases the current I, and vice versa. A decrease in resistance increases the current, which kind of makes sense. If I'm decreasing the opposition of the current, then there'll be more current. If I'm increasing the opposition of the current, then there'll be less current. So kind of intuitively makes sense. The unit of measurement for R, again, we have to give the unit of measurement, again, I'm going to use square brackets, is the ohm. So this is the Greek letter omega, but the unit of measurement is the ohm. So be wary not to call it the omega. It is the ohm. And we can see from the equation above that V is equal to IR. And so when we discuss Ohm's law, we will talk about that a little bit more. And so essentially, in summary, what is a resistor? Well, things that resist. Well, if it resists, it's a resistor. Well, resists the flow of charge, resists current. And so that, like I said, could be a lamp. It could be a diode. It could be anything that resists the flow of current is essentially a resistor. Can behave like a resistor. And the one thing that resistors do, unfortunately, is they generate heat. Well, in some cases, that's a fortunate thing. In some cases, not so much. So we need to talk a bit about the actual heating effect that resistors provide. We call this electrical heating. So basically, in summary, if I have a current, I usually need a resistance, so I'm going to get some unwanted effects. And so if I have a current, I want some resistance. Currents plus resistors usually equal heat. Your old tungsten filament lamps, most of you will be too young to remember, but your tungsten filament lamps heat up more than they light up. They release more heat than they do light. And so if I have a current flowing through one of these lamps, these tungsten filament lamps, let's say there's a current I, and I have an ammeter to measure the current, and I have a voltmeter to measure the voltage. This lamp acts as a resistor, and that resistance will cause the tungsten filament to heat up, and it's actually the heating effect that leads to the lighting effect, not the other way around. And so this lamp will heat up, and that's because there's a current passing through it. Switch the current off, and there isn't any heat through the lamp. Now, the power, we said the energy per unit time that's being consumed by the lamp coming from the battery is VI. But earlier we said that V is I times R. So that's I times R times I. If I just know the current I and the resistance R, I can write this as I squared R. And so if I know the current and the resistance, I can tell the power. If I keep the current constant and I increase the resistance, you can see that heating effect becomes more measurable, becomes greater. And also, P is equal to, well, I can now, in the equation, V is equal to IR, replace the I by V over R, and I get V times V over R. And so this is just another way of writing power, V squared over R. So depending on whether I know the current or I know the potential difference across the resistor, as long as I know the resistance as well, I can tell the power, that is the energy per unit time that is being used by that resistor. And so that's how we can calculate the heating effect of a resistor. Now, the next thing we need to talk about, which we I actually thought this was in DC circuits, but kind of forgotten it was here in this topic, is that of Ohm's law. Now, I'm going to draw a graph of current versus voltage. I know that graphs are not your best friend, and they may not be for a long time to come, but bear with me. I'm going to draw a graph of, well, actually a current versus voltage graph, a current versus potential difference graph. And it's going to have a pretty weird shape. It's going to look straight for some parts, but going to curve at high values of the current in either direction. And this is a graph of current versus voltage, or current versus potential difference. Again, we just say voltage because potential difference is too long of a word to say. So this is a graph of I versus V for a filament lamp, like the lamp I spoke about, the tungsten filament. And what's special about a tungsten filament lamp? We know that it heats excessively. It heats more than it lights. And so there's excessive heating in this conductor. So it behaves as a resistor, but it doesn't behave as a very good resistor because as its heating changes, its resistance also changes and the effects become more pronounced at higher temperatures. But if I draw the same graph, for another type of conductor, this is the graph of I against V, and you can see clearly this is a straight line, but Ohm, the person named Ohm, used a constant tan wire. So a very specific type of wire for which he found that there was no temperature change. Now, the first case is the case of a filament lamp, and there's not a very good mathematical function that I can use to describe this shape. But the second case, I do have a good relationship between I and V. I have a straight line. And so if there's no temperature change for the constant tan wire, then I have a good relationship. So what does Ohm's law say? So from this experiment, what Ohm concluded was that, and I'm going to be lazy, so I'm going to type this out, but what Ohm concluded from this experiment was that for a metallic conductor at constant temperature, so for a metallic conductor, unfortunately I can't type as fast as I can speak, at constant temperature, what happens? The current, as you can see in the graph, the current is directly proportional to the potential difference across the conductor. The current, I should be more specific. The current, and again, you need to know this definition. It could be a 1 or 2 mark question in an exam. The current in the conductor is proportional to the potential difference across that conductor. And basically what I'm saying is that V is proportional to I, which we can see in this figure. V and I, as V increases, I increases, and it does so linearly. And so we say there's a direct proportionality between the two. And the relationship between these V is equal to IR is the mathematical form of Ohm's law, which means that in this graph, I can use the gradient to find the resistance R. So for any conductor that doesn't change temperature, as I vary the current, I should see a vary of the voltage in the same direction. And I measure the gradient, and I can use the gradient to find the resistance. And so that's Ohm's law. But now why is it that when I have a temperature change, I have a difference in resistance? So for the filament lamp, for example. So we need to be able to briefly explain why that happens. So at a higher temperature, what happens? If you know a little bit of basic chemistry, you know that when you heat a substance, the atoms of that substance begin to move more. Heat it enough and it can melt, heat the liquid enough and it can evaporate. And this happens because the actual atoms are moving with more energy. So at a higher temperature, if the atoms are moving more, the electrons, which were initially moving quite freely, have more things to collide with, because now the atoms that they normally were just sidestepping are now getting in their way, and the electrons collide with these atoms, and this increases the resistance. So there's a greater resistance. Try walking through a room when people are stationary. It's much easier than if the people in the move are moving about at random and at high speed. And so that's why high temperature means greater resistance. And there are some other factors that also affect resistance, not just the temperature, but the other factors that can affect the resistance are as follows. So firstly, if I change the length of the wire, if I have a wire that's really long, if it runs the length of the earth, for example, I find that there is a greater resistance. So longer wires mean greater resistance. And this is simply because the electron has, well, more things to move through. If I have to walk through the room with many more people, a much longer room, I am more likely to encounter someone, more likely to collide with someone. And so the electron will experience a greater resistance, so the charge will experience a greater resistance, having to move through that larger, the greater distance. If I increase the thickness of the wire, however, I lower the resistance. So a thicker wire means lower resistance. And why is this so? Because now the charges can move around the things that would normally hinder them. So we said R is proportional to L, R proportional to the length, but the resistance is inversely proportional to the area. If I make the wire very thick, the electrons can now move around those things that are going to be in their way, going to cause resistance. Why am I explaining all of this? Because there's another equation that we can use to define resistance, which has more to do with the material of the wire itself and the structure of the wire. R is equal to a weird letter that looks like a P but is more slanted, rho L over A. This is the Greek letter rho. Looks like a P, but it's actually the Greek letter R. And this rho, make sure it doesn't look like a P, it's more slanted, is what we call the resistivity. Resistivity is constant for a specific metal and is specific for different metals. And the resistivity rho, if I rearrange this equation, is equal to the resistance R times the area of the wire, so the cross-sectional area. If I think of the wire as three-dimensional thing, then there must be a cross-sectional area A. RA over L is equal to rho, and this value for rho depends on the metal. And so different metals, different substances have different resistivities. And the way you can think of it is the lower the resistivity. Again, the word resistivity sounds like resistance. So lower rho means better conductor. You want to have less of a resistance, less of a resistivity as well. So a lower value of rho indicates a better conductor, and a higher value of rho indicates a better insulator. And different materials, like I say, have different values of the resistivity, rho. So that's another equation you can use to find resistance. Or you can use it to also find the resistivity of a certain metal. And from here we can see that the unit of measurement for rho, R is measured in ohms, and area over a length is a length, so that is ohm meters. We don't have a derived unit of measurement for resistivity, so we're simply going to use ohm meter, which is fine on its own. So be careful, the ohm comes in front of the meter purely because if I had it the other way around, it would look like milliohm. So it's the ohm meter. Just be wary of how you write it. The Greek letter, the uppercase Greek letter omega, and a little m. And so the last thing that is part of the learning outcomes for the topic is different types of resistors. So specifically different types of variable resistors, the resistors that can actually vary their resistances. And the first type of these resistors is called a light-dependent resistor, also known as an LDR. So a light-dependent resistor, or an LDR, is a type of resistor that can vary its resistance depending on its temperature. So it's a special type of resistor that we call a variable resistor. And the circuit symbol for an LDR, we will cover this again in the next topic, but it is a resistor symbol which is just a box with two arrows coming down and to the right. And that's an LDR. Now, its resistance is not fixed, unlike the resistance of a fixed resistor. But the resistance of the LDR depends on the intensity of light that falls on it. And so it can vary its resistance, meaning it can allow more or less current to pass through depending on how bright light is being shone on it. So typically, LDRs are made so that higher intensities of light mean that it has a lower resistance. So if the light is very bright, the resistance is lower and current can flow through the LDR. And if you use a logarithmic scale, you don't really have to know what a logarithmic scale is, but basically what you do need to know is that the resistance and the intensity have an inverse relationship. So if I were to sketch a graph of resistance versus intensity, what I find is that at a very high intensity, very bright light will mean a very low resistance for the LDR. And so we can place this in a circuit where we want the resistance to change depending on the amount of light, like a light sensor for an outdoor light. If the light drops below a certain level, the components in the circuit activate to switch on the outside light. But during the day, when the light intensity is high enough, the light remains off. So that requires no physical input. All is done automatically by the sensor. And so if I plot this on a logarithmic scale, I see that the resistance and the intensity are inversely proportional. As the intensity increases, the resistance decreases. The other type of variable resistor, thing that can vary its resistance, vary the amount of ohms that it has, is a thermistor. Specifically, we're going to talk about NTCs, or negative temperature coefficient thermistors. But we're actually going to assume that all the thermistors we deal with are going to be these kinds of thermistors. So we're just going to call them thermistors to be safe. And a thermistor is a device, well, you can probably guess from the word therm, or from the part of the word therm, that its resistance varies with temperature. So the resistance of this device depends on the temperature that is surrounding the device in this circuit. And the circuit symbol is, again, a resistor with a little line like that through it. And you'll learn this in time as you study DC circuits in more detail. And this is the thermistor's resistance, just like the LDR, has a very similar relationship. That is, the higher the temperature, the lower the resistance. Just like for the LDR, the higher the intensity, the lower the resistance. For the thermistor, if the temperature increases of the device, the device's resistance decreases. And you can read up on how this happens, how a higher temperature actually allows current to flow. So remember, thermistors are doing the opposite of what our regular metals were doing. Our regular metals would heat up and increase the resistance. But a thermistor does the opposite. It's made in such a way so that when you increase the temperature, it actually drops the resistance and allows more current to flow. And you could see again why that could be useful. It could be used as a thermostat, or a device to generate or allow or restrict current depending on the temperature of an object. And if I were to sketch a graph of resistance against temperature, I would see that at low temperature I have a high resistance, but as the thermistor's temperature increases, the resistance drops and more current is allowed to move through. And so these are just two types of variable resistors. There will be others that you may come across, but these are two types that you need to know, and you need to know their relationship between the temperature and resistance in the case of thermistors, and light intensity and resistance in the case of LDRs. And so this was a crash course on the topic of electricity. Again, this is only sort of the intro to the intro of DC circuits. But I hope this video helped. If it did, please leave a like, drop a comment, subscribe to the channel. It will help me out. And I will see you again next time on Everything is Relative. That's all for me. I'm Mr. K.